Hi guys, I'm Regina and this is my Lab 1 on charge tapes. For this lab, I've split it up into the introduction where I will talk about the purpose of the lab, models, principles, and the summary. And for the experiment details, I will go over the experiment itself, code, discussion, and conclusion. The purpose of this lab was to understand electric forces and interactions between like and opposite charges, to become familiar with electric field and force calculations, and to build computational models to simulate interactions with GlowScript. Now, in this experiment, the system is tape B, and tape A and the Earth act as its surroundings. For models and fundamental physics principles, we have Newton's second law, which states that the net force of an object is equal to the change in momentum in the net force. We have the velocity update formula, the gravitational force due to Earth's gravity, Newton's third law, which states that for every action there is an equal and opposite reaction, Coulomb's law, or the electric force, the magnitude of the electric force, and Coulomb's constant. The methodology behind this experiment was to create U-tapes by placing one strip of tape on the table and taping another strip of tape on top of the first one. Then pull off the U-tape from the base tape and observe the interaction between the U-tapes and a U-tape with a charged plastic object. Then suspend one U-tape on objects of equal height and lace another U-tape below suspended U-tape. Then observe motion of suspended U-tape and note the separation between the U-tapes. Here, a preview of my results from this experiment. I have some measurements, and my assumptions were that the pieces of tape have the same net charge, have a point charge at the center, and that air resistance is negligible, and my expectations were that the two pieces of tape would repel each other along with my hand. Calculation-wise, I calculated the mass of the tape, the electric charge on the U-tape, excess electrons, number of atoms, and excess electrons over atoms, and my observations were that the tape was attracted to my hand and the negatively charged pen, and it was also attracted to the wooden desk and repelled the other piece of tape. And my conclusion was that the tapes are positively charged. This model here simulates the charges on each piece of tape as a single point charge. I calculated the force of gravity and took the absolute value of that force to estimate the electric force on tape B. I then rearranged Coulomb's law to solve for Q and created two spheres for the tapes along with the gravitational force arrows. I used the electric field function to solve for the electric force. Lastly, I estimated the Q needed by dividing the electric force by the electric field observed on tape A and did the same thing for tape B. This model had the same calculations as I had done by hand, and the charge needed was 1.06 times 10 to the negative 8 coulombs. This model represents the tapes as line charges, meaning that the total charge of the tape is spread across the entire length. The function created a line of 10 spheres with separate points to create each line charge. To calculate the electric force of tape B, I used a function that calculates the electric field at each of the 10 points using superposition with the bottom 10 points. I calculated the electric force on the top tape, adding it to a net total each time. The results we achieved from this shows us that the charge I calculated from the previous model is too small and would need to be spread out like a line charge. Now here I had to find the charge that allows for the magnitude of the electric force to be equal to the magnitude of the gravitational force. You can see that I found the scale factor by taking the square root of the magnitude of the gravitational force divided by the magnitude of the electric force, which ended up being 2.33265, and multiply that by the initial charge, and we got a new total charge that would be spread out among the 10 points. This model now illustrates the magnitude in which the forces are equal. Here are my final results: the initial length and width of the tape, the distance between the tapes, the surface area of the tape, the mass of the tape, the measured electric charge on the tape, the number of excess electrons, and the number of atoms. Some possible errors while doing this experiment could have been when measuring the length and width of the tape, the held U-tape not being parallel to the suspended U-tape, inaccurate measurement of separation distance, or rounding errors when doing calculations. Why would the computational values for Q be different, and which one is most likely to be closer to the real value, and why? So it's different because in the line charge model, it takes in the entire length of the tape versus the point charge model, where it takes one part of the tape, making it all one point, which is not what's happening. And the value closer to the real thing is like the line charge because it's taking in the entire length of the tape. Another discussion question was, what if the signs of the charges were reversed? If that was the case, then the positively charged U-tape would be negatively charged and have an electric field that points towards the tape rather than away. The observations would remain the same. The two tapes would have a negative charge and would have a repelling force on each other. The charged pen would have a positive charge, and its charge is opposite to the tapes, meaning the attractive force remains. Ultimately, the experiment gave me the chance to witness the effects charges have on each other, such as how like charges repel and opposite charges attract, and applying Coulomb's law to calculate charge in an object. Since the tapes are positively charged, they must have been deficient in electrons, and we know that electrons can transfer from objects. Thank you.